This is video 2.11. We're going to talk about Lewis dot diagrams. These are something we're going to use throughout the year, and they're very important. When we get to bonding, we will exclusively be drawing these because they only illustrate the valence electrons. Okay, and those valence electrons, as I've already alluded to, are the only ones that actually do anything when we bond. So they're the most important to us. So there's kind of a step process to go through. There's going to be tricks to kind of help you with this. So make sure you have your periodic tables out. That's going to be very, very helpful. And then follow the process, and this will be super easy, I think, for you. So number one, we're going to write the element symbol. Okay, that's the first thing we're going to do. Number two, we're going to check the electron configuration from our periodic table. The last number in the configuration, as we've already kind of mentioned before, is the number of valence electrons. Okay, so that last number in the sequence is the number that we're going to use for our our dot diagrams. Okay, now you can either use an X or a dot to represent your electrons. You will see me typically use a dot for one, and when we get into bonding, I may start out using an X for the other one, but don't stress about it either way. They just mean valence electrons. So our example we're going to do is carbon. Okay, so look on your periodic table. What's the symbol for carbon? Should be an easy one. It's a C. If you look at the last, and I know mine's on the side here, okay, but if you look at the last number, guys, in carbon, there's 4. All right, so 4 dots are what we need to show, and of course my notes went back. My apologies with this. Guys, we're going to show those 4 dots around this, or excuse me, around the symbol. Okay, excuse me. So typically, how I teach my students to do this is I fill in the first 2 at the top because they represent the s orbital. Okay, so that's just kind of a way to kind of help you remember that, hey, the s orbital fills first, then we're going to fill in the p's around there. Okay, so if you remember to one of the last videos, right, when we have a p, we spread them out first. Now this is just an easy way to kind of help drive home that, hey, the S block fills first, then the P block. But with carbon, especially when you have 4, a lot of times you will see it written like this as well. Okay, and that deals with bonding, which we'll talk about later and throughout the year. So don't get hung up on it right now. Just be aware of knowing the valence electrons and then putting the number of dots around it that it shows. The only way you will double up is if you do it like this on the left, okay, where you do the top first or any side 2 first and then spread them out, or spread them all out all at the same time. Okay, because of Hund's rule, remember, where the electrons want to go into different orbitals first before they start doubling up. Now, if we're working with an ion, think back to yourself. What is an ion, right? It's got a charge, it's got a different number of electrons than it normally has, either gained or lost them. We have to adjust the number of valence electrons, either add or subtract, in the configuration before constructing our dot diagram. The final diagram must include brackets and a charge, guys, because it's an ion. If it doesn't have a charge, then it's not an ion, excuse me, and your structure will be incorrect. So, for example, we have the sulfide ion, S2 minus. Now think to yourself, guys, okay, if it's a negative charge, that really means we're adding, right? Because if we look at sulfur, sulfur has a total of 16 protons minus 2, which is really adding 2, so it has a total of 18 electrons. But when we subtract out and we look at our configuration, guys, it really has 8 valence electrons. So we're adding 2 electrons to it, to the 6 valence electrons that we already have. So 6 plus 2 equals 8. Okay, so when we draw its structure, same thing, same process. Start with its symbol. 1, 2, 3, 4, 5, 6, 7, 8. But since I've added those 2 extra electrons, I have to put brackets around it and a charge on the outside. Okay, if I don't have the charge, like if I get rid of this, guys, that's not sulfur. Okay, sulfur, normally, a neutral atom of sulfur only has 6 valence electrons if you look at your configuration. But by adding 2 extra in, we no longer have sulfur, we have an ion, and we have to include that. Now, one thing to note is that negative ions, or anions, always end up with 8 valence electrons, okay? So anions will always have 8 valence electrons because they're gaining to get to that stable octet, which we'll talk more about throughout the year. Now, this one, potassium, okay, it's +1. Remember, a +1 means that we subtract it. So again, if we look at potassium, normally has 19 minus 1. Oh, now it has 8 valence electrons. Or if you think about valence electrons only, it had 1 valence electron as a neutral atom. Subtract out that charge. Now we have 0 valence electrons. So we are removing 1 electron from the valence shell of potassium. So normally it would have the 1 dot, but now we've removed it, so it's going to have no dots around it and a +1 charge. Again, if you don't have, if you had the dot, or if you just write it without a dot, it's not correct. So you've got to make sure that you have the brackets and the charge. I can't tell you how many times students will forget that. Something easy like that on the reference, or on the Regents, or on a quiz, or on a test, and I have to take points off because it's not correct. All right, so make sure you remember that. Quick note, positive ions always end up with 0 valence electrons showing. I'm going to add that word over here as well. Okay, so cations always have 0 dots, and then your anions will always have 8 dots. All right, so I want you guys to pause the video right now, and I want you to go through and do these 10 elements, then come back and check your work, okay? All right, so I'm going to kind of go through these a little bit quicker and kind of just show you the answers. All right, so argon has 8 if you look at it. This is neutral phosphorus. There's no charge written there, so it would just be 5. Silicon, much like carbon, okay, you could write it as this, or you could write it like I did the first one, okay? Doesn't matter which order. I typically, guys, go clockwise. You could go counterclockwise if you want, as far as putting the dots in. All right, beryllium. Beryllium, guys, those group 2s like that, make sure you have them together again because the S is filling in first. Oxygen, 1, 2, 3, 4, 5, 6. Aluminum's going to have 3. 1, 2, 3. Sodium, he's got 1. Now, anion. Oh, so we normally have 5. We're going to subtract the charge, which really means we're adding it. So we're going to have 8 total. So now it's going to be full. But the last thing I got to remember that I put in there is my charge. Sodium, 1 minus the 1, 0. So it's going to look like this. Okay, we did both of these. These are the same, right? No, they're not. So make sure that you have to show the difference because something's happened. It has a charge. And then oxygen, again, these guys look the same, but we normally have 6 minus 2, which is really adding. So we have 8 valence electrons that we're going to show. And that has to have the charge. All right. So the number, just a quick note, we'll get more into this when we get into bonding. The number of unpaired valence electrons, VE is valence electrons, is equal to the number of bonds that an element can form, all right, which we'll talk more about. When determining the number of bonds of an element that it can form, arrange valence electrons so that you have the maximum number unpaired. Again, that'll come more later on, so don't stress about that right now. So for example, carbon, right, the maximum number of unpaired valence electrons would be something like this. We would write it out like that, so now that we can form a bond there, 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 and there. But again, that stuff will come later, so don't stress about it. Carbon can form 4 bonds, okay? The alternate Lewis structure for carbon with only 2 unpaired valence electrons represents the lowest energy state, okay? So when we kind of pair some things up, that's representing a lower energy state to some extent. Now, one last note. You will not be tested, guys, on your reagents with any full noble gas or orbital notations. The purpose of these is to make bonding easier later in the year. You will be tested on the basic ones. So the last few videos, I realized, like, why on earth? It's going to make bonding easier. All right, so just note that only the basic configurations back here in video 2.7, those will be the only ones you will see on the reagents. Till next time, I'll see you later.